Good afternoon, everyone. Today we're going to look at an application problem with rational equations. And the situation is that two yakkers can paddle downstream 18 kilometers when they're going with the current in the same time that they can go 8 kilometers upstream traveling against the current. Now, the current in this river is flowing at a rate of 3 kilometers an hour. So we are looking to find how fast can they paddle in still waters when there would be no current in theory, okay? So to do this, I recommend making a table with the information that you're given. Okay. So we know, first of all, that speed, velocity, is measured as distance divided by time, right? And so we're going to make a table with speed, with time, and with distance. However you want to organize those three values, it's up to you. Now we're going to do, let's say first we'll do with the current in the first row. We'll go against the current in the second row. And we'll go in still waters in the last row, okay? And we're going to break it up like so. And we are going to fill in the pieces of information that we can, kind of like when we're solving a puzzle, kind of like solving a Sudoku, I guess. So the distance that they are traveling when they're going downstream with the current is 18 kilometers. The distance that they are traveling when they're going against the current upstream is 8 kilometers, but it's in the same amount of time. And that's very important to note, because that means that the time that they're traveling upstream and downstream is set. It's equal to one another. And so that means that we can call that, we don't know how long it takes, but we can call that some time t for both, okay? Now, the distance when they're going with the current is going to be 18 kilometers. And the distance that they travel against the current, because they're going slower, is only 8 kilometers. And so the current flows at 3 kilometers an hour. So that means that their speed with the current is going to be, well, first of all, let's figure out what we want to find. What we're looking for is how fast they're paddling in still waters. So we want to know their speed in still waters. We're looking for this value down here. Let's call that V, okay? That's the one we're looking for. V, speed in still waters. And our units are kilometers, and they are, well, they're kilometers per hour, so let's measure this speed, obviously, in kilometers per hour, okay? That's our V. Now, that's our V in still waters. If that's defined in this way, then the speed that they'll be paddling when the current is pushing them along at an additional 3 kilometers an hour is going to be V plus 3, right? And their speed against the current, when the current is pushing back against them and making it harder for them to move forward, their speed is going to be reduced by 3 kilometers an hour, right? Because the current is acting against them. And so now we have some way of relating all of our unknowns. It's not this row that's going to help us, but because we have two rows and we have two unknowns, namely t and v, this is going to allow us to set up a system of equations. Okay, so what I would do from here is I would note again that v is equal to d over t, and so that means that the speed is equal to the distance over time. Right? Now, that also means if I do a bit of algebra, if I multiply by t, then I get that v times t is equal to d, and then if I divide by v, I get that t all by itself is equal to d over v, meaning that time is equal to the distance divided by the speed, right? That should make sense. And I do that because we have time as t in both rows. That means that from the first row, we can set up our first equation that t is equal to d over v, meaning 18 over v plus 3. So t is equal to 18 over v plus 3, and that comes from the information in row 1. Now in row 2, we get again that t is equal to d over v, so the distance, 8 over the speed of v minus 3, so 8 over v minus 3. And now, I'm guessing you're used to solving systems of equations by, I should label my second equation. Call that equation 2 from row number 2, right? So now we have a system of equations, we have two unknowns, t and v, and we have two independent equations. And so we should be able to solve for both, okay? Now, I'm guessing you've learned substitution elimination. Clearly, we already have a variable that is isolated. This is perfectly set up for substitution. So let's go ahead and do that. Since we have t isolated in both, we can simply say that in general terms, t must be equal to t. And that means that 18 over v plus 3 has to be equal to 8 over v minus 3. It has to be, right? Because the time is set in stone and t is d over v, right? And so now we get a rational equation. So to solve this, we're going to multiply both sides by both denominators. So I'm going to multiply by v minus 3 times v plus 3, and I'll do times v minus 3 times v plus 3, like so. Now, on the left-hand side, the v plus 3 factor is going to cancel out, and so we'll have 18 times the factor of v minus 3, right? And on the right-hand side, the v minus 3 factor is going to cancel out, and so conversely, we'll have 8 times the factor of v plus 3, like so. And now we have a really straightforward equation to solve, right? We're going to multiply through the brackets, as we always do, like so. And so we'll have 18v minus 54 is equal to 8v plus 24, right? And we can solve that. We can subtract 8v from both sides. We can add 54 to both sides. All right? Yeah, sure. And so we get 18v minus 8v is 10v equals to 24 plus 54 is 78. Like so. And you guys guessed it, we divide both sides by 10. 10's cancel out. And we get our solution that v is equal to 78 over 10, meaning that v is 7.8 kilometers an hour. And there we have it. That is our speed, v, that we defined to be the speed in still waters in kilometers an hour, and that's what we were after all along. So, I hope this helps, and thank you so much for watching.